partial fractions. In this section, we're going to show how to integrate any rational function. Recall that a rational function is a function that looks like a quotient of polynomials by expressing it as a sum of simpler fractions that we know how to integrate. Those simple fractions will be referred to as partial fractions. Okay? To illustrate this method, let's make the following observation. Let's take a look at equation asterisk. 1 divided by x minus 1 minus 1 over x plus 2. If you take the difference, take a common denominator, you combine the two, you're going to find the right-hand side of asterisk. Now, if you reverse the procedure, and let's say you would like to integrate the right-hand side of asterisk, it's the same as taking the difference of the two integrals, right? As you're seeing here at the bottom of the screen. So if you would like to integrate this guy, it suffices to integrate 1 over x minus 1, and you also integrate 1 over x plus 2, and then take the difference between the two. Correct? And this one is easy to integrate, obviously. You can use direct substitution here. You can set the variable to be x minus 1, and integrate regularly here, and obtain that this is ln of absolute value of x minus 1, and this is similarly is going to be ln of x plus 2. Okay? So decomposing, if you start from here and you are able to decompose it, then it's done, right? You can easily integrate it. Alright, so how does this method work in general? To see how this method plays out in general, let's consider a rational function f of x to equal p of x over q of x. So p of x is the polynomial upstairs, and q of x is the polynomial downstairs. Okay, it's possible to express this function, the quotient, the rational function, as a sum of simpler fractions, provided the degree of the numerator, which is p, is less than the degree of the denominator, which is q. So one more time, if you are able to so if the numerator has degrees smaller than the degree of the denominator, then what this is saying, then I'm going to be able to express the function f as a sum of simpler fractions, like we did above. For example, here in this one. So upstairs is the p guy, that's the p guy, right? And the degree of this guy is just 0, right? Because it's a pure constant. And q, the denominator, is this guy. And the degree of x squared plus x minus 2, it's the degree of the leading term, which is x squared, so it's of degree 2. So certainly the degree upstairs is smaller than the degree downstairs, 0 being smaller than 2. Correct? And as such, I was able to decompose this into the difference of two simpler quotients, where each one is easy to integrate. Okay? So what this is saying is that's going to happen as long as the numerator has degrees smaller than the denominator. Okay? So let me highlight this for you. So it's possible to express f as a sum of simpler fractions, provided that this is the case, right? Okay. And such a quotient, meaning when the polynomial upstairs has degrees smaller than the denominator, the polynomial downstairs, such a rational function is referred to as a proper rational function. Okay? So proper rational function means the numerator has degree smaller than the degree of the denominator. Okay. Now, otherwise, if that's not the case, meaning if f is improper, and improper means not proper, so the degree upstairs is going to be at least the degree downstairs, right? So if f is improper, how can we proceed? Well, what we can do is we can take the preliminary step of dividing p by q, right? If you divide p by q using the Euclidean division or the long division, it's the same, until a remainder r of x is obtained. And the remainder can be made of degrees smaller than the divisor, which is q. Correct? So this is something you learned in college algebra. So it's always possible to divide two polynomials where the dividend is of degree bigger than the degree of the divisor. And you can obtain a remainder whose degree is smaller than the degree of the divisor, which is q in this case. So you get this. So you get this one, right? Okay. And what happens to the quotient? So this quotient p of x divided by q of x becomes the quotient, so s of x, right? So let me put it in perspective. So you are dividing p of x using long division, correct? By q of x. You're gonna obtain a quotient. In this context we call it s of x, and the remainder r of x. The remainder is of degree smaller than the divisor, right? So this is what this is saying. And then you can write p of x divided by q of x, so this guy, the function f of x, is going to be equal to s of x plus the remainder over the divisor, q of x, right? So you're going to get this. And look at this rational function here. What can you tell about this rational function? This is proper, right? This is proper. Why this is proper? Because the degree of r, the numerator now, is smaller than the degree of the denominator q. Okay? So this becomes proper. So let's actually write this down. So this becomes proper. Okay? And this is proper. Alright, so what have we done? What have we discussed so far? So what this highlighted one is saying, if you have a rational function whose numerator is of degree smaller than the denominator, then you are able to write this quotient as a sum of simpler quotients, right? And hence if you want to integrate this function f, you're going to integrate those simpler quotients, which are going to be easy to do, like we did in this little example here, right? Now, if the rational function is not proper, which means you have the degree upstairs bigger than the degree downstairs or equal, what you can do is you can divide p of x by q of x, obtain a remainder whose degree is smaller than the divisor q, and as such this part of the division statement is going to be proper. So you can now decompose it. You can run the highlighted lines. You can run this discussion here for this proper quotient. Okay, so by the highlighted discussion here, you can say that I can rewrite this guy as a sum of simpler quotients. Okay. All right. So as the following example, example 1, demonstrates, sometimes this preliminary step, which is long division, is all that's required. Let's take a look. This quotient here, this quotient is certainly not proper, right? Because the numerator is of degree bigger than the degree of the denominator. So this is an improper rational function. So we're gonna run into this preliminary step, which is long division. We're gonna divide the numerator x cubed plus x by x minus 1, right? And I hope you remember how to do long division. Let's do it. So I'm gonna multiply x by something to get x cubed, and that thing is x squared, right? X squared times x is x cubed, and x squared times negative 1 is negative x squared. Correct? And then I'm going to take the difference. And what do I obtain? So I obtain x cubed minus x cubed is 0, they're gone. And I get x minus the minus, so plus x squared. So x squared plus x, if you write it in a descending fashion for the exponents. Correct? So you get x squared plus x. Now you're gonna multiply x by something to get x squared, and that guy is x, right? So if you multiply x by x, you get x squared. And if you multiply x by -1, you get negative x. Okay? And now if you take the difference, what do you get? We obtain x squared minus x squared is 0, they're gone. X minus the minus x, so it becomes x plus x, and x plus x is twice x, right? So that becomes twice x. Same game. Now I'm gonna multiply x by something to get 2x, and that guy is 2, right? 2 times x is twice x, and 2 times -1 is -2. And now if you take the difference, you obtain 2x minus 2x is 0, and 0 minus the -2 is +2. Correct? So that's the remainder. That's the remainder. And what was the label of the what was the label of the remainder in the discussion upstairs? It was R, right? It was R. So that's the R. So that guy is the R. And that guy was the P of x, right? This guy is the Q of x. And who's this guy? That's the S of x, right? That's the S of x. So this guy is the S of x. That's the quotient, right? It's right there. Okay, so you can now write P of x over Q of x as S of x plus R of x divided by Q of x. So thus, the primitive of x cubed, actually before we talk about the primitive, let's talk about the quotient. So x cubed plus x divided by x minus 1, right? This is equal to, this guy is equal to S of x, which is the quotient, so x squared plus x plus 2, plus the remainder over Q of x, and the remainder is 2 divided by Q of x, which is x minus 1. Correct? All right. And now if you want to integrate this guy, that's the objective here. If you want to integrate this guy, x cubed plus x divided by x minus 1, right? So x minus dx, this is then equal to this, the integral of this polynomial, which is x squared plus x plus 2 dx plus 2, okay, all right, so let's push the 2 outside, 2 times the primitive of 1 over x minus 1 dx. Agree with this? So all this discussion right there is actually for the long division. Let's isolate the 2. Okay. All right, so back to this. This is easy. So primitive of x squared is x cubed over 3 plus 1/2 x squared plus 2x plus twice the primitive of 1 over x minus 1. We talked about it above. This is ln of absolute value of x minus 1, right? Plus a constant of integration. And you can take the 2 as an exponent and round the bars. It's okay. I mean, this is an answer, right? So what have I done here? I wanted to rewrite this as a proper quotient, proper rational function. So I appealed to long division, and once I did long division, I got to a point where I'm integrating, instead of integrating this rational function, I'm integrating now a polynomial and this proper rational function, which is easy to integrate, right? So this proper rational function is actually easy to integrate, and then I'm done after this point. Okay. So what was the first step in integrating an improper rational function? it was just using long division, right? Because, I mean, improper rational function means the numerator is at least the degree of the denominator. So the first step was use long division, get to a statement where you have that function f equal to a polynomial s of x plus a proper rational function. And now what's the next step? Once you are down to here, what's the next step? In the first example, we saw that the next step, there is no next step because that guy was very easy to integrate. But in general, how would we handle this if that proper function r of x divided by q of x is not as easy as we obtained? So how can we handle it? Well, the next step is to factor the denominator q of x as far as we can. Okay, so the denominator downstairs, we're gonna factor it as much as possible. It can be shown that any polynomial q may be factored as a product of linear factors of the form ax plus b. Linear factors means factors of the form ax plus b, power of x is 1, and irreducible quadratic factors. Quadratic factors are a polynomial of degree 2, right? But being irreducible, it means you cannot factor it over the real numbers. So that is to say, its discriminant b squared minus 4ac is negative. Okay, so this is a very important discussion here. Any polynomial, it may be shown that any polynomial q, so the proof of this thing is beyond this course. So any polynomial q may be factored as a product of linear factors and a product of irreducible quadratic factors. Okay, so linear factors means of this form, quadratic factors means of this form, and being irreducible, it means that the discriminant b squared minus 4ac is negative. Okay, so this is a crucial statement here. All right, so that denominator q of x, right? So that denominator q of x and the proper rational function, that denominator q of x, we're gonna factor it as much as possible. And we know that, according to those three lines, we know that once you factor it, you're gonna either obtain product of linear factors and factors which are irreducible quadratic factors. Okay, so they are of this form where the discriminant is negative. All right. For instance, consider the following q of x: x to power 4 minus ad1. So you can factor this by looking at this as a difference of two squares, right? You can think about x to power 4 as x squared and ad1 as 9 squared. So you get the difference of two squares. So this can be thought of as x squared minus 9 times x squared plus 9, right? Okay. And one more time, we can factor x squared minus 9. This is still a difference of two squares. So this can be factored as x minus 3 times x plus 3, this part. But this guy cannot be factored anymore. This is an irreducible quadratic factor. It cannot be factored anymore. The discriminant in this case, a is 1, b is 0, and c is 9. So 0 squared becomes 0 minus 4 times a times c. A and c are both positive. With that negative, everything is going to turn into a negative, right? So the discriminant of this guy is negative, and as such, it's an irreducible factor. This is just to illustrate those three lines. So x4 minus ad1 factors as linear factors. These are linear factors, power 1 of x, right? And quadratic factor, which is irreducible. You cannot factor it anymore, right? This is what it means to be irreducible. It cannot be reduced anymore. It cannot be factored anymore. Okay? And remember from basic algebra, college algebra, quadratic polynomials that have negative discriminant cannot be reduced, cannot be factored anymore, right? Okay. All right. So this is the next step. This was the next step. So one more time. The first step was The first step was, if you have an improper rational function, you take long division, so you turn this improper into a sum between a polynomial, which is easy to integrate, and a proper rational function. Then the denominator q is going to be factored as much as possible, and this tells us that once you do so, you're going to either obtain linear factors of this form or irreducible quadratic factors of this form, and we gave an example. Now the last step, the third step, is to express the proper rational function, this guy, right, Rx divided by Q of x, the guy that we were just discussing, that guy. So is to express it as a sum of rational functions of the form this or this. We'll discuss this those two in more details just shortly. But those guys are gonna be constants divided by constants, right? A is a constant here, divided by powers of linear factors. These are linear factors. So one more time, constants. So a constant divided by a power of a linear factor, or linear factors, a linear factor divided by power of irreducible quadratic factor. Okay, so remember that the denominator is gonna factor at the end of the day as product of linear factors that look like this and product of irreducible factor that look like this, where the discriminant of those guys are negative. So what you can do, and we'll talk about this shortly in details, but what you do at the end, you can rewrite Rx divided by Qx. You can rewrite this proper rational function as a quotient that looks like this, or a quotient that looks like this, right? As a sum of combinations of these. So those guys are constant divided by powers of linear factors. Realize that the numerator here is smaller than the degree of the denominator, right? I'll talk about degree 1 here, degree 0 upstairs, and degree, if I is 1, the degree here is simply 1, right? So either constant divided by powers of linear factors, or linear numerator, so a linear numerator ax plus b divided by powers of irrational second degree factors, right? So powers of quadratic factors, which are irreducible, right? So observe here is if k is 1, the degree upstairs is still smaller than the degree downstairs, right? Okay. All right, and a theorem in algebra guarantees that this is always the case. We can always do this. 4 cases are in order. So case 1, what if q of x, remember we have to factor q of x, the denominator where? The denominator in here, right? The denominator in here, we need to factor it. So a case among those 4 cases that I was just alluding to, the first case is once you factor q of x, you get a product of distinct linear factors. So you can write one situation is once you factor q of x completely, you factor it into linear factors, but more than this, they're all distinct, right? So meaning that they don't repeat, right? So there's no one linear factor that's repeated, okay? And by repeated, I mean not even having a multiple of that linear factor, okay? So case 1, once you factor q of x, the denominator, you're gonna get factors that such that they're all linear and they're all distinct, okay? For example, abstractly speaking, if you're talking about q of x and it factors as such, here I'm assuming that none of them repeat, so they're all distinct. And none of them is a factor of another, right? That's what I mean as well. So in this case, the partial fraction theorem states the following, that there exist constants. The number of those constants is going to be the same number of those distinct factors. In this case, how many distinct factors I'm considering? 1, 2, 3, 4, etc. all the way to n. So here I have n distinct linear factors in the Q of x that I'm giving, right? I have n distinct linear factors. So what the partial fraction theorem states, I'm gonna be able to find n constants. So there exist a1 through an, they're all constants, such that this proper rational function r of x divided by q of x can be written in this fashion. So a1, that constant a1, divided by the first linear factor, this is the first linear factor, plus constant a2 divided by the second linear factor, plus etc., all the way to the last quotient is going to look like an, that constant, divided by the last linear factor. Okay? And if you want to integrate now this guy, you're going to integrate each of those, right? But each of those is easy to integrate. It's going to have to do with ln, right? Okay. Let's take an example. Let's evaluate x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x. So in this case, the numerator is of degree smaller than the denominator, so it's already a proper integral, right? A proper rational function. So this is already proper. So that's already proper, right? Okay. So which means you can now factor the denominator. Q of x in this context is 2x cubed plus 3x squared minus 2x. And let's factor it as much as we can. According to what we just discussed, we're going to obtain product of linear factors and irreducible quadratic factors, right? We may not get all of them, but the worst we're going to get is product, bunch of linear factors and bunch of irreducible quadratic factors. Let's see which of those we get in this case. So let's factor that out. I realized that x is a common factor, so let's push it as a common factor. 2x squared plus 3x minus 2. Correct? So this is a linear factor. This is of the form, I can think about x as being 1 times x minus or plus 0, right? This is a linear factor. The power is 1. Okay? All right. And this is quadratic, but this quadratic is reducible. You can factor that. The discriminant is not negative. You can factor that guy. As a matter of fact, you can use quadratic formula and obtain 2x minus 1 times x plus 2. Okay? So you factor it as such. So we factored q of x as much as we can, and what did we obtain? We obtained 1, 2, and 3 linear factors. And they're all distinct, right? They're all distinct. This is the first linear factor, this is the second, and this is the third. None of them is repeated, which means that they're all distinct. So this q of x falls in case 1. Q of x is a product of distinct linear factors. Correct? How many linear factors do we have in this case? In our context, we have 3. 1, 2, so 1, 2, and 3. We have 3, right? And according to the discussion that we just had above, the partial fraction theorem says we're going to have now 3 constants, such that the quotient r of x divided by q of x is going to look like one of those constants divided by the first factor plus the other constant divided by the second factor plus a third constant divided by the last or the third linear factor, right? So according to what we just discussed, then this guy, so this guy, x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x, based on case 1 discussion above, we're going to be able to find three constants. Let's call them, instead of calling them A1, A2, A3, how about ABC? We can call them A1, A2, A3, but let's call them ABC. So A divided by the first factor, who's the first factor? Let's say x, plus another constant B divided by 2x minus 1, the second factor, plus a third constant C divided by the third factor, which is x plus 2. Correct? Do you agree that this is what the previous discussion was saying, case 1? So this proper fraction, right? This proper fraction is going to be a constant divided by one of those guys. What are those guys? Those are the factors, plus another constant divided by another factor, and so on. Correct? That's what I have. Okay, so where A, B, C are to be determined, right? So where A, B, and C are real numbers to be determined. Based on the discussion above, these three constants are guaranteed to exist, but we need to find them. So are real numbers to be determined, right? TBD. All right? Okay, so how do we determine those constants A, B, C? Let me start with the most obvious one. How about we make the same denominator on the right side of this equation? Okay, so let's find ABC. I'm gonna make the same denominator on the right side. So how about we call this guy equation something? So about equation star. Okay. All right. So equation star then becomes equivalent to x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x equal, I'm gonna have the same denominator on this side. And what's a common denominator among these? It's x times 2x minus 1 times x plus 2, right? I'm just taking the product of the denominators. And what am I left with upstairs? A times, so I multiplied this x by 2x minus 1 times x plus 2 to have that denominator being that guy. So I'm going to multiply upstairs too, right? So 2x minus 1 times x plus 2. Plus, for b, I multiplied by x downstairs to make this common denominator. I multiplied downstairs by x times x plus 2. And for c, you multiply downstairs by x times 2x minus 1 to get that common denominator. So I gotta do it on the numerator as well. So c times x times 2x minus 1. Okay. All right. And don't forget that guy downstairs, the 2x cubed plus 3x squared minus 2x, is x times 2x minus 1 times x plus 2, right? So they are the same. They are the same. So this piece and this piece are the same. And then what can you say? What can you say? So this becomes equivalent to, if the two denominators are the same, then the two numerators must be the same, right? X squared plus 2x minus 1 should equal to a times 2x minus 1 times x plus 2 plus bx x plus 2 plus c times x. Let me make some room for myself here. So cx times 2x minus 1, right? So I kind of cancel that common denominator. So the numerators have to match. Okay. All right, so what am I doing? I'm after a, b, and c. I need to find a, b, c that verify equation star, right? So equation star is equivalent to this, which in turn is equivalent to this as long as the denominator is not 0, right? And I'm after a, b, and c. Okay? All right, why am I after a, b, and c? Because once I find them, I can put them here, over here the a, over here the b, over here the c, and then since I wanted to integrate that guy, then I'm gonna integrate each piece, and it doesn't take you more than a second to realize that each one is easy to integrate, right? They're gonna all have to do with ln. So the primitive of a over x, a is a pure constant, so you push it outside the integral, and then dx over x is ln of the absolute value of x, and so on and so forth. Correct? So once you find a, b, and c, technically you're done. It's just a little more effort, and then we integrate. And then we're done. Okay? Alright, so I just wanted to go back to the big picture. Okay, so let's keep going after a, b, and c. So that's equivalent to, this is a second degree polynomial, right? And this is a second degree polynomial as well. For them to equal each other, they have to be they have to be of the same degree, and they will be, but each coefficient of the corresponding term, the corresponding power of x, have to match as well, right? So let's find what each side is and match coefficients. X squared plus 2x minus 1 is equal to a times, let's FOIL this out, 2x times x is 2x squared, 2x times 2 is 4x, minus 1 times x is minus x, minus 1 times 2 is minus 2, right? Plus b times x squared plus 2x, here I just multiplied each one here by this x, plus c times 2x squared minus x. I'm still here, I'm distributing the multiplication over subtraction, so I get this. Okay, all right, and this is equivalent to x squared plus 2x minus 1. I want to match coefficient by coefficient, right? So the coefficient of x squared is 1 here. What's the coefficient of x squared here? Let's find that out. So what's the coefficient of x squared here? Well, the ones that have x squared that have to do with x squared are this guy and this guy and this guy, right? Okay, so this is gonna be multiplied by a, so we're gonna get 2ax squared. So we're gonna get 2ax squared. This guy is gonna be multiplied by b, so bx squared, so plus bx squared. I'm factoring x squared at the same time. And this guy I have to do with 2cx squared, correct? So factor out the x squared, you get this. Okay, so this is the coefficient of x squared then. Now, moving on to the coefficient of x. So I'm gonna have a coefficient for x. And what's that coefficient? What are those guys? That have to do with that x? They are this and this over here, right? Let's actually combine those two. How much is this? This is 3x. So it's this guy, and this guy, correct? And what do we obtain? This is gonna be 3x times a, so it's gonna be 3ax, so 3ax, plus this is gonna be multiplied by b, so 2bx, so 2bx, and then the last one is gonna be minus 1 times cx, so this is gonna be minus cx, right? Okay, and then the constant part, let's put it here, the constant part. And who's the constants? We have minus 2a. We don't have constant here, so just minus 2a. All right, let me actually just erase this part and just write it by itself, minus 2a. Correct? That's the only constant I have. Everything else is gonna be either in terms of x or in terms of x squared, so they were accounted for here. Okay? So now this polynomial, this is a polynomial, and this is a polynomial, right? They are of the same degree, so the only way they can match is if the coefficients match. So one has to match this, 2 has to match this, and -1 has to match -2a. Correct? So this is what's happening. Okay, let's do it. So therefore, 1 should match 2a plus b plus 2c, and 2 should also match 3a plus 2b minus c, and -1 should match minus 2a, right? So this should happen, and this should happen. So it's like solving a system in 3 variables, right? This last one is immediate. This last one tells me immediately what a is. A is certainly 1/2, right? So I got my hand on a. A is half, just divide by -2. Okay, so a is 1/2. Now I'm gonna rewrite those two equations, which were in 3 variables. Now I'm gonna have to replace a by what it is to turn these two equations in 2 variables and try to solve them, right? Okay, so these guys then become equivalent to the following. 1 is equal to twice a is 1, right? If a is half, twice a is 1, plus b plus 2c, and this becomes 2 equals a is 1/2, so 3a is 3/2, plus twice b minus c, right? And if you focus here, it's just 2 equations in 2 variables, so it should be easy to be done. All right, one more time. How did we get to this point? In this equation, this side is a second degree polynomial, this side is a second degree polynomial. The only way they match is if their coefficients match. So 2a plus b plus 2c should match 1, 2 should match this, and -1 should match -2a. This gives me immediately what a is, and then I use this new knowledge and replace what a is in those 2 equations to turn them into 2 equations in 2 variables now. Now I just have b and c in these 2 equations, right? So I'm gonna solve this small system. Okay, so just to make room, let me just take these 2 guys over here and put this on top. Okay, so I can have more room. All right, and those 2 guys are equivalent to what? So 1 equals 1 plus so this is b plus 2c equals 0. Correct? This side, if you subtract by 1, you get b plus 2c equals 0. And this side, you get what? You get 2b minus c is equal to 2 minus 3/2, right? If you subtract by 3/2 both sides. 2 minus 3/2. 3/2 is 1.5. 2 minus 1.5 is a half, right? This is a half. 2 minus 3 over 2. If you do the same denominator, which is 2, so you get 4 minus 3, which is 1 over 2, right? Okay. So you get this. You can finish it using your own perspective. What I'm gonna do is I don't know. So how about replacing b by -2c upstairs? So, well, in the first equation here, I can say that b is certainly -2c, right? This means b is -2c. And let me organize myself. So So that equation is equivalent to this. So this and this are equivalent, correct? And then if you use this knowledge now in the second equation, so this entails that 2b minus c, 2b minus c, if b is negative 2c, then twice b is gonna be negative 4c, right? So twice b is gonna be negative 4c minus c, which is minus 5c, and how much is 2b minus c? How much is 2b minus c? Is half. So this guy is half, so this guy should match half, right? Okay, so this top equation gave me b equals negative 2c. I replaced b by negative 2c here and got this guy minus 5c. Negative 5c should be 1/2. That is to say, c should be negative 1/10, right? Correct? Again, you don't have to follow this method. Just do your, however you think about it, just do it. So c is this much. So how much is b then? If c is negative 1/10, so b is going to be negative 2 times the negative 1/10, so it's going to be plus 1/5, right? So this forces b to be negative 2 times the negative 1/10, and b is, at the end of the day, positive 2/10, which is 1/5. Correct? So b is this much. So b is this much. A is this much. And c is this much. Correct? So now if you go back to equation star and you plug in what a, b, and c are, then you integrate to get that integral that we wanted, right? So let's give this integral a name. As usual, let's call it I. Okay. All right, so this is my I. And in equation star now, so in equation star, so equation star becomes the following. The right side, the left-hand side of the equation was x squared plus 2x minus 1 divided by x 2x cubed, right? 2x cubed plus 3x squared minus 2x. Okay. Equals the a, and the a is 1/2, so it's gonna be the a, so 1/2 divided by the x, right? Plus the b, and the b is 1/5 divided by the 2x minus 1 plus the c. How much is the c? Negative 1/10. Negative 1/10 divided by the last factor. The last linear factor was x plus 2, right? Okay, so let me just see if this is correct. So the a over x, the b is over 2x minus 1, and the c is over x plus 2, right? Okay, so this is correct. Okay. And then if you want to integrate this guy, which means you are looking for I, right? We call the primitive of this to be I. That's going to be the primitive of half, so that's a constant, 1 over x dx plus the 1/5 primitive of 1 over 2x minus 1 dx minus 1 over 10 primitive of 1 over x plus 2 dx. Correct? And as I promised you, each one's going to have to do with ln. Let's do that quickly. This is then equal to 1/2 times ln of the absolute value of x plus 1/5 times, and here we're going to do the mental, let's do it mentally. So I'm going to do 2x minus 1 to be the variable u. So du would be 2 dx, right? So 2 dx. So it's going to have here, I'm going to have to multiply by 1/2. So that's going to be 1 over 10. Primitive of, so 1 over 10 twice, that's what I'm saying. So I'm going to multiply by 2 here, and I'm going to multiply by 2 here. Those cancel, so we're back to the same thing. So if you call this guy u, that's going to be, so du would be 2 dx, so you get this, and that's going to be du over u, which is ln of the absolute value of u, right? Which is 2x minus 1. So regular direct substitution here, minus, this is minus 1 over 10 ln of the absolute value of x plus 2, right, plus a constant of integration. Okay? Alright, so this is I then. So this is I. So let's summarize the steps. So we started with an I, it was proper. If it weren't proper, how should I start it? I should have started by going through the process of long division to set the stage for having, let me take you back to that. Where is it? So if I don't have a proper fraction, I'm gonna go to long division, and the division statement is gonna say I'm gonna have polynomial plus a proper fraction, right? But in this case it was proper, so I didn't have to go through long division. Okay, so this was proper, and the next step is to factor the denominator as much as possible. So I factored, and what happened here is I'm getting as factors linear factors. Each one was linear factor, and each of the factor, all the factors are distinct, right? So meaning there's no linear factor that's repeated, and this puts me in case 1, correct? So this puts me in case 1, and case 1 gives me a description on how to handle such a situation. This proper fraction now is gonna look like something like this, where each numerator is a constant, and the denominators are these linear factors. The linear factors here are just x to x minus 1 and x plus 2. So I'm going to have x to x minus 1 and x plus 2 as those denominators. And the numerators are going to be constants. And we went into the trouble to actually find those constants. A, B, C. It's guaranteed. I mean, the partial fraction theorem states that A, B, and C are going to exist, right? The problem is, in each concrete situation, what are they? So this is what the next discussion was about. So we found them. We found that A was this much, C was that much, and B was this much. And then we went to equation star, did this, and integrated easily, right? Each of those partial fractions, remember, each one is called partial fraction. Each of those partial fraction is easy to integrate, and then we found our desired integral. Okay, so these were the steps. All right. There is, in the process, we found ABC through this long method. There is an easier way to find ABC. Let me discuss it. So that easy way is gonna be from, let me highlight that. So it's gonna be from this point here. Okay. All right. So let's call this guy let's call this equation here, let's give it a name. How about double asterisk, or actually double stars, because we start with a star here. So double star. Let's call this blue box, this blue box equation, let's call it double stars. Okay. So what's double stars? What's double stars? I'm gonna copy it. So this discussion is about an alternative way. So this is an alternative way to find the constants. Alternative way to find A, B, and C. Okay. All right. So let's paste the equation. This is it. Oops. Let me delete it again and paste it here. Okay. So this is the equation double stars, right? This is what we call as double stars. Okay, so double stars hold for all real numbers, right? So double stars hold for all real numbers. So for all real numbers. X. So no matter what x you replace with, you should get a true statement here, right? So the double star equation holds for all real numbers x, right? So let me put that over here and let me make everything blue. Okay, so this holds for all real numbers x. Now let's choose x. Let's choose x so it allows this part of the equation to vanish. Such an x can be taken to be 0. So for when x is 0, when x is equal to 0, because this holds for all real numbers x, right? So because this holds for all real numbers x, I'm gonna choose an x to be suitable that for simple calculations to find those coefficients. And I'm choosing x to be 0. Why? You're gonna see, because it's gonna make this guy 0. Double stars becomes what? If you replace x by 0, you get 0 squared, so 0 plus twice 0, 0, minus 1. So the left hand side is simply minus 1. The right hand side is a times 2 times 0. Remember, I'm replacing x by 0. So 2 times 0, that's 0 minus 1. So minus 1. And 0 plus 2 is 2, right? Plus, that guy is 0 because x is 0. So it's going to allow this to disappear. And 0 as well here is going to make this disappear. So the 0, right? I'm going to write it. So look, this tells me minus 2a is minus 1. It puts me right there. It puts me right here, right? So I'm done with a. So a is half. Make sense? So a suitable choice of x allowed me to just say, okay, so that's your a. So that is a is half. Does this make sense? So we just because this holds for all choices of x. I mean, choose an appropriate one that simplifies matters for you. And x equals 0 allows this to go and this to go, and then everything else is going to remain for a, right? All right, now for b. I want to find b, right? And to find b, what I'm going to do is going to allow this guy to vanish and this guy to vanish. What type of term they have in common? The 2x minus 1 is in common. And what's the number that allows such a guy to vanish? 1/2, right? 1/2. If you replace x by 1/2, this vanishes and this vanishes. Correct? Let's do that. So now when x is half, double stars that equation becomes what? It becomes, let's do it here. So 1/2 squared is 1/4 plus 2 times the half, the x is half, 2 times half is 1 minus 1 equals, don't forget, this term is gonna vanish. Let's double check. So replace x by 1/2. 2 times 1/2 is 1. 1 minus 1 is 0. So this guy becomes 0. So this whole thing now is 0. This is gone. Similarly, this is gonna be gone, right? Because if you replace x by 1/2, that guy is 0, and this 0 times whatever number you have is 0. So both terms are, both expressions are have vanished here, this one and this one. The only survivor is the b guy. So it's gonna be b times the x, and the x is half, times the x plus 2, and if x is half, x plus 2 is gonna be 5/2, right? 5/2. Okay, and this is equivalent to saying that 1/4, because 1 minus 1 is 0, so 1/4 is equal to b times 5, so 5b over 4, right? So 5b over 4, that is to say b is, so that is to say b is 1/5, right? And that's the same b we found before. It's the same b that we found before, correct? And I hope by now you understand the game. So for x, for c, I'm gonna now make a suitable choice for x so that those guys vanish. And what's common to both guys? It's the x plus 2, right? So choose the x so that this term x plus 2 vanishes, which means x equals -2. So once you choose x to be -2, this guy is gone, this guy is gone. The only survivor on the left side is gonna be the c term. Okay, so I'm gonna take then, I'm gonna choose x to be -2, and then double stars becomes what? So the left side is gonna be -2 squared, so the square of -2, which is 4, right? Plus 2 times the -2, so -4, okay, minus 1 is equal to, as we said, if you choose -2, this guy being -2, this whole thing is gone. So that whole thing then is vanished. Similarly, this guy has vanished because when x is -2, that's gone. And then we're gonna be left with c times -2, right? C times -2 times, I'm replacing x by -2. 2 times -2, that's -4 minus 1, that's -5, right? That's -5. Okay, and this means that -1, because 4 minus 4 is 0, so -1 is equal to 10c. 10c. So that is to say c is the -1/10 that we found above, right? The c, right? The -1/10. Okay. All right. So this is an alternative way to find a, b, and c. And what was the way? The way was we focused on double star, the double star equation, namely this guy, and we said that this is this holds for all choices of x, right? Okay. Now you may object. You may say, well, this guy, the double star equation, is coming from this guy, right? So that's equivalent to this guy, that equation. And this equation used to hold as long as the denominator is not 0, correct? Which means this equation holds for all x that are neither 0, right? The denominator is 0 when x is 0, nor when and for x different than 1/2, because the halves allows this factor in the denominator denominator to be 0, and for x different than -2. Correct? And for x different than -2. So for all these three guys, so for x different than 0, and for x different than 1/2, and for x different than -2. And then you're gonna tell me, oh, so this equation, the double star, should hold for all the x that are different than the 0 and the 1/2 and the -2. And how did we choose it? How did we choose those x's to be those guys that do not allow double star to hold? Okay, so I'll summarize again what might be an objection. So the idea is, we said double stars, the double star equation is equivalent to this cloud thing, right? And this thing, this equation, which is sitting in this cloud, is an identity. It holds for all x that makes the denominator not 0. So which means this holds for all x and r, for all real numbers x, such that x is not 0, x is not half, and x is not -2, correct? Because these are the guys that make the denominator 0. So this identity should hold as long as x is not 0, x is not half, and x is not -2. So double stars then should hold for those x's. This double star equation should hold for all these x's that are neither 0 nor half nor -2, right? So how then did we do the following? Since double star should not hold for those x's, for this guy, and this guy, how were we able to actually choose them? Okay, so that's the point that I'm trying. I'm just saying, what if somebody says the following? My answer would be an exercise that goes like this. So if you object what I said earlier, this would be the exercise that I want you to do. So exercise, let P, Q, and R be three polynomials Here I'm not talking about P, Q, and R being the ones that we just discussed above. These are random polynomials, arbitrary ones. So three polynomials such that P of x over Q of x is equal to R of x divided by Q of x. So suppose that these three polynomials have the following property, and this property, assume it holds for all x in R, such that Q of x is not 0. Okay, so suppose that this identity holds for all these numbers that do not make the denominator 0. Show that P of x is actually equal to R of x, not for those x which are in R but do not make the denominator 0, for all x in R. So show that actually those guys, P of x and R of x, are the same for all real numbers, even for those which make the denominator 0. That's what I'm saying here. Okay? So one more time. If P, Q, and R are three polynomials satisfying this identity, for all real numbers that do not make the denominator 0, the denominator being Q, show that actually the numerators P and R, the two guys upstairs, are actually the same for all real numbers. So including those which make the denominator 0. Okay? So by this exercise, think about it, and we'll talk about it in class, obviously. So we're gonna talk, this is left as an exercise, and we'll discuss it in class. Okay? So because of this exercise, then now I go back to here, to this bubble, right? And those two quotients are the same. This would be like the p of x, this would be like the q of x, and this numerator here would be the r of x, right? This is the same q. This guy downstairs and this guy downstairs are the same, right? This is just a factored version of this guy. So the situation is exactly as in the exercise. P of x over q of x is equal to r of x over q of x for all those numbers x such that the denominator is not 0. So they are x different than 0, x different than half, x different than -2. And by the exercise below, then p of x, the numerator here, is going to match the numerator here. So r of x for all x, right? For all x. For all x. So what I said here then is correct. So what I said here is correct. Okay? And because it holds, this identity holds for all real numbers x, I'm allowed to choose any x I want, and hence my choices. So these were appropriate choices. Okay? Alright, so let's now move on to the next exercise. This is on page 557, number 8 from the book. Let's try to find the primitive of x cubed minus x plus 3 divided by x squared plus x minus 2 dx. So in this case, this quotient, this rational function is improper, right? Because the numerator is of degree greater than or equal to the degree downstairs. So the first step would be to go through the long division, the Euclidean division, right? So I'm going to divide x cubed minus x plus 3. I'm going to divide it by x squared plus x minus 2. Okay? So the first question is, what should I multiply x squared with to get x cubed? And that's simply x. X times x squared is x cubed. And x times x is x squared. And x times -2 is -2x, right? Now if you subtract the bottom from the top, we obtain what? X cubed minus x cubed is 0. For x squared, I'm going to get -x squared, right? I'm going to keep writing them in a descending fashion for exponents. So -x squared. For the x term, I'm going to have minus x plus 2x. So minus x plus 2x is plus 1x. And the constant term is plus 3, right? Okay. Now, for the next part, I'm going to multiply now x squared by something to get -x squared, and that thing is -1. So -1 times x squared is -x squared. -1 times x is -x. And -1 times -2 is plus 2. Okay? And now if you subtract the brown thing from the brown expression from the green one, we obtain this minus itself is 0. X minus the minus x is twice x. 3 minus 2 is 1, right? So 2x plus 1. That's the remainder. And the remainder is of degree smaller than the divisor. Okay, so we stop here. And then this integral, so let's call it a j. So thus, actually, let's talk about the rational function. Okay, so let me just make some room for myself here. So, based on this discussion, we can say that x cubed minus x plus 3 divided by x squared plus x minus 2 is equal to, so this guy is equal to this time the divisor times the quotient plus the remainder. So if you divide this dividend by this divisor, you're gonna get the quotient, which is x minus 1, plus the remainder, which is 2x plus 1, divided by the quotient, which is x squared plus x minus 2. Okay? So based on this discussion on the side, we got this, right? Okay, let's do it this way. So then j is, which is the primitive of that, it's going to be the primitive of the polynomial x minus 1 dx plus the primitive of 2x plus 1 divided by x squared plus x minus 2 dx. Am I correct? So the next step over here is to, in order to integrate that rational function, one way to do it is to factor the denominator as much as possible, right? To factor the denominator as much as possible. So, which is x squared plus x minus 2, because at this point, this fraction, this rational function is actually a proper fraction, a proper rational function, because the numerator is of degree smaller than the denominator, right? So now I want to write this, as partial fractions, correct? So we shall now write the partial fraction decomposition of the proper rational function (2x plus 1 divided by x squared plus x minus 2). Correct? So the first step is, as we said, to factor out the x squared plus x minus 2. This is the q of x guy, right? This is the q of x. That guy is the qx. So qx is guaranteed to split as product of linear factors, as we said above, product of linear factors and product of quadratic factors that are irreducible. This guy is not irreducible, this is reducible. The discriminant here is positive, right? b squared minus 4ac is positive. It's actually 1 plus 8, so 9, right? So the discriminant is 9. So you're gonna have integers as its so this is gonna split over the integers actually. Q of x is gonna be x plus 2 times x plus 1. Correct? So if you FOIL this out, you're gonna get, oh sorry, there's a sign here, x minus 1. So x squared plus 1x minus 2, so you get this. So qx splits as such, and clearly each of the factors is linear and they're distinct, right? So q of x factors as distinct linear factors. Correct? One of them is x plus 2 and the other one is x minus 1. They're distinct, they're not the same. So this is in case 1. Case 1 handles this situation. What was case 1 again? Let's go back there. Case 1 was, once q of x splits as distinct linear factors, then you're going to be able to find constants. You're going to be able to find constants. The number of constants is going to be the same as the number of factors. In our context now we have 2 factors, right? So we have one of the factors is x plus 2, the other one is x minus 1. So 2 factors. So I'm going to be able to find two constants so that this proper rational function is going to look like a constant divided by one of the factors plus another constant divided by the other factor, correct? So let's go back to our page. So therefore, the 2x plus 1 is going to divided by x squared plus x minus 2 is going to factor as a constant divided by one of the factors, which is x plus 2, plus a constant, doesn't have to be the same, probably another one, times x minus 1, right? So I'm going to let you discover what the constants a, b, and c are. I'm going to give you the answer immediately. So find that the b and the a are, let me write it in a different color. So check that a actually happens to be 1 and the b is equal to 1 as well. Okay, so they're both 1. So they're both 1. If you take them both 1, you're going to get x minus 1 plus x plus 2, and x minus 1 plus x plus 2 is 2x plus 1, and downstairs you get this. So this is correct. Okay, and the process is as you did in the other one, as we did in the other one. Okay, so we get that this is a 1 and this is a 1, and therefore j is equal to, so j is this, right? It's gonna be now the primitive of x minus 1 dx plus the primitive of this guy, which is 1 over x plus 2 dx, plus the primitive of this guy, which is 1 over x minus 1 dx, right? Okay. All right, each one is simple. So this one is x squared over 2, so 1/2 x squared minus x plus natural log absolute value of x plus 2 plus ln of absolute value of x minus 1 plus a constant of integration. Okay, so this is j. So what did we do? We did long division to pick up that proper rational function. This is easy. That's a polynomial. So for this one, we factored out the denominator as much as we can, and we obtained distinct linear factors. And once we obtained distinct linear factors, now we know exactly how this proper rational function actually splits as a sum of partial fractions, and then find a, b as we did before. And how do we find a and b? We gave a couple of methods above. You can have the same denominator and find a and b. I mean, any of the two methods described above. And then once you find a and b, it's going to be 1 and 1, and then we're done, right? So we integrate and we're done. As a matter of fact, in this problem, it could have been done in an easier way. We don't have to go through partial fraction decomposition. So take a look at this. This may be integrated via a different approach. Realize that the derivative of the guy downstairs is the guy upstairs, right? So the derivative of x squared plus x minus 2 is 2x plus 1. It's the guy it's the guy upstairs. So actually there is a different way to find this guy. Okay, so let's give it a name. How about we call this guy W? Okay. All right, so let's find W via a different way. So an alternative way approach to find W. So W was the primitive of 2x plus 1 divided by x squared plus x minus 2, right? Dx. And if we do simple direct substitution here, if we let u to be x squared plus x plus minus 2, then du becomes 2x plus 1 dx, right? Correct? So this becomes du, and therefore w then becomes the primitive of du over u, right? Which is ln of the absolute value of u. Agree with this? And how much is u? How much is u? U is x squared plus x minus 2. Right? That's w. That's w. So technically w, according to the previous discussion, technically this is what w is, right? This is what w is. That guy. That guy was w. Or is w. Correct? And the result for that was this. This is what w is. I mean, up to the constant, right? So I should add the constant here. Let's add a k constant. My point is that's a primitive. That's primitive for 2x plus 1 divided by x squared plus x minus 2. And then this should be this then, right? This should be this up to a change of up to a constant. So this should be this up to a constant. And do you see why? Look, this guy is equal to, if you want to make the case that this guy and this guy are actually the same, this is ln of the absolute value of x squared plus x minus 2. We said it splits as x plus 2 times x minus 1, correct? This is not what we said. This guy, right? So x squared plus x minus 2 is x plus 2 times x minus 1. So we get this. And ln of a product is the product of the logs. So ln of x plus 2, an absolute value, I should say, an absolute value. Because we don't know what x is, plus ln of the absolute value of x minus 1. Correct? Plus that constant. Okay. Makes sense? So I just use that the log of a product is the sum of the logs. So we got this. And now probably it's easier to see that they are the same, right? They are the same up to the constant, up to a constant. And that constant is combined, right? It's combined with the constant that this integral brings, and we called it c at the end of the day. The whole constant part is called c. Okay? So this would be an alternative approach to find that guy w. So the going through partial fraction decomposition was not necessary, even though it was a good practice. Okay? So let's keep going. Remember when we discussed about the steps? So the second step was to factor out that guy q of x, which is the denominator, right? So we're talking about this guy, right? R of x divided by q of x. Once we get the proper fraction or proper rational function, we're gonna factor out q of x as much as possible, right? And we said it's gonna split as a product of linear factors and irreducible quadratic factors. And we said here we have 4 cases that are in order. Case 1, we dealt with it. That case was q of x splits as product of distinct linear factors. The second case is, what if I have a linear factor that's repeated? Correct? That's going to be the second case. So let's go to that. So case number 2, if q of x split as a product of linear factors, they're all linear factors, but some of them are repeated. Some of them are repeated. Let's suppose that the first one is repeated, and let's suppose that it's repeated k times. Okay? So let's suppose it's repeated k times. That is to say, that guy to power k occurs in the factorization of q of x. Correct? That's what it means. That's what it means for a linear factor to be repeated k times. This factor to be repeated k times. It means that that factor to power k occurs in the factorized version of q of x. Okay? Now, what the partial fraction theorem says, instead of having a single quotient, we used to have a constant divided by that linear factor, right? Instead of having this, now we're gonna have all of this. All of this. So we're gonna have, instead of a1 divided by a1x plus b1, we're gonna have the structure of all of these are gonna be the same, but the denominator is gonna be taken from power 1 all the way to that power k, which is the amount of repetition of that factor. Okay? So, one more time. If we have one of the linear factors that's repeated k times, let's say k times, where k is a natural number. So, instead of having a single term that looks like a constant divided by that linear factor, now we're going to have k partial fraction pertaining to that linear factor. And the structure is going to be a constant divided by the linear factor to all the powers from 1 all the way to that number k, and then you're going to add them up. Okay? So let's say, for example, I have k is 3. If k is 3, then I'm going to have a constant divided by a1x, that linear factor to power 1, plus another constant divided by that linear factor to power 2, plus one more guy, a3, so in this case there are no dots, divided by that linear factor to power 3. Okay? So by way of illustration, let's read this thing that comes here at the bottom. By way of illustration, we may write the following. X cubed minus x plus 1 divided by x squared times x minus 1 cubed. Well, number one thing to point out here is that this is a proper fraction, right? Why it's a proper fraction? Because the numerator upstairs is degree smaller than the denominator downstairs. What's the degree upstairs? It's 3, right? What's the degree downstairs? This is of degree 2 times the degree 3. So 2 times the degree 3, you're going to have of degree 5, right? The x squared, when it talks to the x cubed term, it's gonna yield x to power 5 term, right? So the degree downstairs is 5, degree upstairs is 3. So certainly this is proper. And because it's proper, we're going to factor the guy downstairs. It's already factored for us. And then by case 2 that we just described, because here I have two linear factors, namely one of them is x, the other one is x minus 1. So the x guy is repeated twice and the x minus 1 guy is repeated 3 times. Correct? So for the x guy, I'm going to have a constant divided by x plus a constant divided by x squared. So I went from power 1 all the way to that power, which is 2. Okay? And now for the x minus 1 factor, it has 3 copies of it. It's repeated 3 times. So I'm going to have to go from power x minus 1, from this power all the way to power 3. So from power x minus 1, from x minus 1 to power 1, all the way to power 3. So I'm going to go 1, 2, 3. And then the numerators are going to be constants, right? Like this is saying. Okay? Alright, so let's move on to the next problem. Example 4. Find the primitive of this rational function Clearly this rational function is improper because the numerator is of degree smaller than the denominator, so we have to do long division, right? I'm not going to do it, I'm going to just tell you the answer because you know the process by now. So using long division, we obtain the following: x to power 4 minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1. So let me tell you what you're going to find if you use long division. You're going to find that this is equal to x plus 1, that's going to be the quotient, plus the remainder is going to be 4x, and that guy x cubed minus x squared minus x plus 1, right? That's q of x, correct? That's q of x. Let me highlight that. So this is q of x. Okay. So what's the next step? We're going to factor out q of x. And how do you factor this guy? Well, one way is to look for a root. You realize that q of 1 is 0, right? So to factor q of x, observe that q of 1 is 0. Okay, so this entails that x minus 1 is a divisor, so divides q of x. You learned this in college algebra. So if a polynomial has a root, then x minus that root is going to divide q of x. And what was this theorem? That says the following. The name was the Factor Theorem, right? So by the Factor Theorem that you learned in college algebra. Okay. So we found a root. For q of x, namely 1. And the theorem I technically appealed to is called, also learned in college algebra, and it's called rational zeros theorem. And if you recall what this says, if a polynomial has a rational root, then it's going to be of the form a divisor of the constant term divided by a divisor of the leading coefficient, correct? In this case, both leading coefficients and constant terms are 1, so the only possible rational roots for q are plus and negative 1, right? So we checked the 1, it worked. So for sure x minus 1 is going to be divisor of q of x by the factor theorem. What does it mean? If you divide q of x by x minus 1, you're going to have a second degree polynomial that you're going to be able to still use the quadratic formula for it and use and find the other two linear factors. Okay, so since x minus 1 divides q of x, as I said, the q of x then is gonna be written as, let me change back the color. So the q of x then is gonna be written as x minus 1 times a second degree polynomial, right? A second degree polynomial, because if you multiply this with this, you're gonna have a third degree polynomial. So this is gonna be a second degree polynomial. How do you find this? You can perform long division between q of x and x minus 1. So divide x minus 1 into q of x. You get, you're gonna get that second degree polynomial, and this is actually equal to x squared minus 1. X squared minus 1. Okay. So let's do it this way. All right. Now, is this reducible? Yeah, x squared minus 1 is the difference of two squares, so that's gonna be then x minus 1 times x plus 1, right? Another x minus 1 then. So another x minus 1 times x plus 1. So we get this. So here we have q of x splits as linear factors, but in this case one of them is repeated two times. Correct? So 4x divided by q of x then. So 4x divided by q of x. So r of x divided by q of x. And q of x is all this guy. So x cubed minus x squared minus x plus 1, right? So this is by the second case, you're going to be able to find a constant a and a constant b and a constant c, but the first two are going to be needed for the x minus 1 and its second power, right? So this is pertaining to this guy, plus c for the last guy, x plus 1, because it's needed only once. So x plus 1 is by itself, like in case 1 here, and the factors x minus 1 to power 2, because it's repeated twice, that this is when case 2 kicks in, and you're gonna have one fraction that has x minus 1 as its denominator and another fraction that has x minus 1 squared as its denominator, right? So what I'm saying is this, right? Instead of having a single one for that linear factor, you're gonna have a couple, right? Because k in this case is 2. So instead of having k ones, I'm gonna have just a couple. So from power 1 of that linear factor all the way to power 2. This is what I had here, right? Okay. So you get to this point, and then you find a, b, c using a way that we discussed above, and you're gonna find that a is, let me tell you what a, what b, what c are. So check that. Let me just take a moment to see what a is. So a happens to be 1. B is gonna be 2. And C is gonna be -1. Okay, so check that this is the case. So just play the game of taking the same denominator and comparing the two polynomials on both sides, etc. You find that a, b, and c are as such. Okay, so what does it mean then? Therefore, now if you go back to the integral that was given, okay, so let's call it integral y. So if you go back to that integral that was given, now we are in a good position. What do we know about the integrand now? The integrand is equal to x plus 1 plus this guy, but this guy, the proper rational function, now splits as such. Correct? So the integrand then, let me zoom out, and so the integrand, which is this, so therefore, one more time, the integrand, which is all of this, I'll copy it. So let's copy that and paste it here, make it blue. Okay, so is equal to the pink part, which is x plus 1, that's the polynomial, the quotient, plus this piece, which is this guy, right? The proper rational function, which is this guy. We know what a, b, and c are, so it's going to be a, which is 1 over x minus 1, plus the b, which is 2 over x minus 1 squared, plus the c, and the c is -1, so it's going to be -1 divided by x plus 1. Okay? So this is the integrand. Now, how about y? Y is going to be the integral of the sum of the integrals, right? So it follows that y is equal to the integral of x plus 1 dx plus the integral of 1 over x minus 1 dx plus the primitive of 2 over x minus 1 squared dx. Let's push that 2 outside, so keep that constant above 1. And the last one is minus the primitive of 1 over x plus 1 dx, right? Okay. Alright, so let's do each one by itself. This part is polynomial, easy, so x squared divided by 2 plus x, correct? And let's keep the constant combined at the end. This guy is ln of the absolute value of x minus 1 plus 2 times the primitive of 1 over x minus 1 squared. You can use a U-substitution here, just direct substitution. Let u be x minus 1, du becomes dx, right? And this becomes primitive of u to power negative 1 dx, primitive of u to power negative 2 du. And if you integrate that, you get u to power negative 1 divided by negative 1, which means negative 1 over u, right? So negative 1 over u, and the u is x minus 1. I'm doing mental substitution because by now we should be we should do these things quickly. But if you're not comfortable, feel free to just, do it in steps, obviously. Okay, so minus 2, the minus is coming from this guy. You know what? How about keeping the plus and just to highlight the fact that this minus is coming from this. Let's do it this way. Okay, so minus 1 divided by x minus 1 minus, this is ln, right? ln of absolute value of x plus 1 plus a constant of integration. Okay. All right, and you can leave this as an answer. Another way actually is to, how about we combine the ln's together just to revisit one of the properties of ln's. So I kept this, I'm gonna copy this now, minus 2 divided by x minus 1. And now this guy, ln of x minus 1 minus ln of x, the absolute value I should say, ln of absolute value of x minus 1 minus ln of absolute value of x plus 1, both of these yield, this is the difference of the ln's, so this is ln of the quotient, right? The quotient of the two absolute values, and the quotient of absolute values is the absolute value of the quotient, so x minus 1 divided by x plus 1 plus a constant of integration, where c is an arbitrary constant, right? So where c is an arbitrary. All right. So let's go back. Case 2 was, so case 1 was what? Case 1 was the denominator q of x splits as product of distinct linear factors. This was case 1. Case 2 was q of x, the denominator splits as linear factors, but some of them are repeated. So we're talking, remember, we're talking about this piece, right? The proper rational function. Once we do long division and so on, we put ourselves in a proper rational function. We split q of x. If when we split q of x, we get the context of k1, which means denominator, the q of x is product of distinct linear factors, we know how to handle. Now, if we get some of them are repeated of those linear factors, we also know how to handle by case number 2. That's case number 2. And then the third case, remember we have 4 cases. The third case is the denominator q of x contains irreducible quadratic factors, and none of which is repeated. So q of x now contains, among its factored form, irreducible quadratic factors. What does irreducible quadratic factor mean? Quadratic factor means it's a second degree polynomial, and irreducible means it cannot be reduced, which means its discriminant, b squared minus 4ac, is negative. We discussed that way earlier, right? We discussed that in here. So irreducible quadratic factor means it's a second degree such that its discriminant is negative, which means it cannot be factored anymore. Okay? Alright, so what happens in this case then? In case 3, when you encounter such a Q, then the following happens. In addition to what have been discussed before for partial fractions decomposition, the expression for R of x divided by Q of x, that proper rational function, will have a term of the form like this. It's gonna have so one of the partial fraction is gonna look like this. Okay, where this guy is the irreducible factor, and a and b are to be determined, are constants to be determined. Make sense? So let's give an example. Just for instance, if you have this proper rational function, x divided by all of this. Certainly this is proper, right? The numerator has degree 1, the denominator has degree what? 1 plus 2 plus 3 plus 2, so it's of degree 5. So certainly this is a proper rational function. So we're gonna split the denominator. It's already split. This is linear factor. This is second degree. This is quadratic factor, but this is irreducible, right? I'm talking about x plus 1 right there. This guy, this is irreducible. Its discriminant is negative. The a is 1, the b is 0, the c is 1. So certainly the discriminant is negative. Similarly for this, x2 plus 4 is also quadratic and irreducible, right? So I have two factors. Both of them are distinct, and they occur just once, and they are irreducible. Okay, so what I'm gonna have for x minus 2, for this guy, case 1 handles this, and what does it say? The corresponding partial fraction is gonna look like constant divided by this guy, correct? So this takes care of this. This guy takes care of this. Now, for this guy, x squared plus 1, it's not repeated, right? That's the only irreducible second degree polynomial of which looks like x squared plus 1. It's not repeated. So this guy is gonna be by case 3, just discussed right now, it's gonna look like ax plus b divided by that guy, right? So obviously because the a is taken, I'm gonna call it bx. I'm gonna call it bx plus c, correct? So bx plus c divided by this guy. Okay, so this guy takes care of this piece. And then the last one, x squared plus 4, this is also irreducible. Let's change the color. So this is also irreducible, and it's not repeated. And the corresponding one, the corresponding partial fraction, also by case 3 is gonna look like this, right? Obviously a and b are taken now, so we're down to d. So dx plus e divided by this irreducible guy, which is x squared plus 4, correct? So we're gonna get this. So this guy takes care of this. Does it make sense? So this sum here would be the partial fraction decomposition of this proper fraction. Okay, let's take an example. Example 5. Let's evaluate 2x squared minus x plus 4 divided by x cubed plus 4x. So this guy, this integrand is proper because the numerator is of degree 2, and that degree is smaller than the denominators. The degree downstairs is 3. So no need for long division here. For the long division step, we're gonna go into factorizing x cubed plus 4x. That's the q of x guy, right? That's the q of x guy. So the q of x, which is in our context x cubed plus 4x, can be factored as x. This is simple, just factor out an x squared plus 4, right? X squared plus 4. And clearly this is an irreducible one, right? Clearly this guy is irreducible. So this is quadratic. So quadratic factor. That's irreducible. Because its discriminant is negative, right? What's the discriminant here, since we're talking about it? The a is 1, the b is 0, and the c is 4. So we have b squared minus 4ac in this case is 0 squared minus 4 times a, but the a is 1 as we said. So 1 times the c, which is 4, the constant part. Oh, sorry, 4, right? Certainly this is like negative 16 or something. This is negative. Correct? Okay, so this is why this piece is irreducible. And then what's the way to write this integrand, r of x divided by q of x? So then this guy, if we copy it, okay, so this guy is gonna be equal to, we have linear factor and second degree polynomial, which is irreducible. So for the linear one, by case 1, this is not repeated, so it's case 1. So by case 1, it's gonna look like a over x, right? This one takes care of the x, plus for this guy, case 3 tells me that's gonna look like, case 3 tells me that the corresponding partial fraction is gonna look like constant x plus another constant divided by that second degree polynomial that's irreducible. I mean, the choice of a was taken. How about bx plus c then? So how about bx plus c divided by that second degree polynomial that's irreducible, which is x2 plus 4. Okay? Alright, so you play the same game. You take, same denominator here and compare the two polynomials, and you're gonna find a, b, and c. So let me give you the a, b, and c. So check that. The a happens to be 1. The b is gonna be also 1. And the c is gonna be negative 1. Okay, so a is 1, b is 1, and c is negative 1. So check that whenever you try to do it. And therefore, the given integral, this one, so this integral, how about we copy it? So this integral alright, so that one is equal to the primitive of the a is 1 over x dx plus the b is 1, so primitive of x, so the c is negative 1, minus 1 divided by x squared plus 4 dx, right? Okay. Alright, this one is easy. That's ln, so ln of absolute value of x. For this one, I'm gonna split them in 2, right? I'm gonna split them in 2. One is gonna look like x divided by x squared plus 4 dx, and the other one is gonna be 1 divided by x squared plus 4 dx. Okay. How about this integral? How do we find this primitive? How do we find this primitive here? Well, if you do the mental substitution x squared plus 4 to be u, right? If this is u, du becomes 2x dx. So x dx is half du. So it's going to be half ln of the absolute value of x squared plus 4. Correct? If you do U-substitution to be x squared plus 4. And then the question is, do I really need the bars? Do I really need the bars? Because x squared plus 4, what do you know about x squared plus 4? Well, x squared is at least 0, so x squared plus 4 is at least 4, right? Which is positive. So x squared plus 4 is already positive, you don't need the bars, right? So I'm gonna put rounded bars as opposed to vertical bars, okay? So I'm gonna have something like this, and that's gonna be this piece. How about this piece? How about now this piece right there? Primitive of 1 over x squared plus 4, think about 4 as 2 squared, right? So this has to do with arctan, correct? So I hope, I mean, if you look at the formulas that you have, this is an arctan thing, right? So it's du divided by u squared plus a squared. So it's gonna be 1 over a, so 2, 1 over a, which is 2, times arctan u, which is x, divided by the a, which is 2, right? So we get this, okay? And now if you put things together, this is nothing but ln of the absolute value of x plus half ln of x2 plus 4. Sure, this is the same as ln of square root of x2 plus 4. Let's keep it this way. Minus 1/2 arctan, or tan inverse, of x over 2 plus a constant of integration as usual, right? Okay, so to evaluate this integral, we factored, again, this is proper rational function. We factor this guy, and we got one linear factor which is not repeated, and we got one quadratic factor which is irreducible and not repeated. So this guy is handled by case 1, this guy is handled by case 3. And then once we got down to this point, this guy is gonna split. One of them is gonna have to do with ln, and the other one is gonna have to do with arctan. And this is always the case whenever you have an entity like this and you try to integrate it, right? You split it in two pieces. One have to do with arctan, and the other is gonna have to do with ln. Okay. All right, and then you add the constant of integration at the end. Let's now evaluate this integral. This integrand is a rational function, but this is not proper, right? This is not proper. So let's use long division. It's not proper because the numerator is of degree greater than or equal to the denominator, right? In this case, they are equal. So this is improper. So as such, the first step would be to use long division, right? So we're gonna use long division. To obtain the following. If you divide 4x squared minus 3x plus 2 by this denominator, which is 4x squared minus 4x plus 3, you're gonna find a polynomial which is now of degree 0. That's gonna be a 1 here, plus the remainder is x minus 1. If you do it, divide by this guy, right? The divisor, 4x squared minus 4x plus 3. Okay, so now this is proper. This is now proper, correct? And what's next? Next is to try to factor 4x squared minus 4x plus 3. If you try to factor this denominator, which is referred to as q of x all along in this discussion, in this lecture video, right? We always refer to this guy as q of x. In this case, q of x, if you try to factor it, you're not going to be able to. This is already irreducible. If you try to find the discriminant b squared minus 4ac, that's going to be negative. Check it. b is negative 4, so b squared is going to be 16 minus 4 times the 4, so 16 times 3, which is 48. So 16 minus 48 is certainly a negative entity, right? So this is irreducible for sure, and as such, the partial fraction decomposition technique cannot be applied. Okay? So instead, we gotta do something else. So what we're gonna do is, we're gonna rewrite this as, we're gonna complete the square for this guy. Okay, so we're gonna complete the square for this guy, and if you complete the square here, you're gonna find, how do you complete the square? So how do you complete the square? So this is 4x squared minus 4x. This looks like 2x plus 1 squared, right? Or minus 1 squared. 2x minus 1 squared. And how much is this? How much is this guy? This is 4x squared, right? This squared minus 4x plus 1. So we added 1, so we got one of those three guys. So 1, we brought it here to pick up this. So I'm gonna lose it back. So we're gonna get just plus 2 here, right? So we're gonna get just plus 2 here. Correct? So I completed the square. I got that guy. And then this integral becomes, so therefore, this integral, the one that we have, so this is the integrand. Let's copy it. Okay, so that's the integrand. Okay, dx is equal to the primitive of 1 dx, so it's x, right? Plus the primitive of x minus 1 divided by 2x minus 1 squared plus 2 dx. Okay? Alright, so how do we handle this? This suggests to have 2x minus 1 as a substitution. So let's introduce let's call the variable t to be 2x minus 1, and this means that dt is twice dx, right? Twice dx. Okay. And how about x minus 1? How about x? So this also entails that x is t plus 1 over 2, right? So solve for x here. This is the same actually, that x is t plus 1 over 2. Correct? So what's the point now? The point is to simply integrate this guy. The point is to simply integrate this guy, right? So how about calling it, let's give it a name. Oops. So let's call it v. Okay. So we're gonna find v, and to find v, that's what I'm doing. To find v, that's what I'm doing. So we shall find v next, right? Okay. So introduce this, and therefore v becomes the primitive of, so we said the x is t plus 1 over 2. So t plus 1 over 2, that's the x, minus 1, and the whole thing is divided by t squared plus 2, and the dx is half dt, right? The dx is half dt. Let's put it this way. Okay? Let's put it this way. Alright, let's clean up some constants here and see what happens. So this is then equal to, if you do the same denominator here, let's do it in different color. If you do the same denominator, which is 2, you gotta multiply this guy by 2. So this becomes half. With this half outside becomes 1/4. 1/4. And what's upstairs now? T plus 1 minus 2 is t minus 1, right? T minus 1 divided by t squared plus 2 dt. Okay? Alright. So next I'm gonna split like I did before, right? Remember remember this thing here? So over here from this to those two. So what did we do? We split them, right? One had to do with ln and the other one had to do with arctan. That's exactly what's going to happen. So we're going to split them. The 1/4 is going to remain there, common for both. And I'm going to have, the first one is t over t squared plus 2 dt. And the other one is 1 divided by t squared plus 2 dt, right? Okay. Actually, I changed my mind. I'm going to take it to the next page because I need to highlight things. Alright, so one has to do with ln and the other is going to do with tangent, arctangent. Let's pay attention to this. If you make the mental substitution to be t squared plus 2, right? T squared plus 2 to be like a new letter z. So 2t dt is going to be dz, right? So half dz is going to be dt t dt, right? Divided by the z. And that's ln of z, ln of the absolute value of z, right? So ln of the absolute value of z, and z was taken to be t squared plus 2. So absolute value of t squared plus 2 is the same as rounding those bars, which means parentheses, right? Because this guy is at least 2. We discussed that before when we talked about the x squared plus 4. I forgot, right? Was it x squared plus 4? Yeah, this guy. So we didn't need the bars because this guy is at least 4, which means positive. Similarly here, t squared plus 2 is at least 2, so this guy doesn't need the bars. Okay. And this piece, this is of the form dt over t squared plus a squared, right? You can think about 2 as square root of 2 squared. So that's going to be 1 divided by a, so square root of 2, times arctan, the variable, which is t divided by a, which is square root of 2, plus a constant of integration. Okay? So, and the formula I'm alluding to is the following. Primitive of dz over z2 plus a2, right? So this guy is equal to 1 over a is not supposed to be 0, so 1 over a tan inverse of x or z over a, right? That's the formula that's actually needed right there. Correct? Okay. So, putting things together, this guy then is equal to 1/4 times 1/2, which is 1/8, ln of t squared plus 2 minus the 1/4 times 1 over square root of 2, so 1 over 4 square root of 2, arctan of t divided by square root of 2. Correct? Don't forget the t was something we introduced. The t was something we introduced. It was 2x minus 1, right? It's right there. It's over here. The t was 2x minus 1. We introduced it to the problem. So let's change back what t is. So 2x minus 1. So I'm gonna have, that's gonna be 1 over 8 ln of, so t is 2x minus 1, so 2x minus 1 squared plus 2, right? What did I do? I changed what t is here. So I changed what t is. T was 2x minus 1. Okay. All right. Minus 1 over 4 square root of 2 arctan of that x, that t, which is 2x minus 1 divided by square root of 2. Okay. All right. Okay, and you can FOIL this out. So this is actually the same guy as we had here, right? It's the 4x squared minus 4x plus 3. Let's write it. So this is 1 over 8 ln of this guy, which was 4x squared minus 4x plus 3 minus 1 over, let's not rationalize the denominator, let's just keep it like this, arctan of 2x minus 1 divided by square root of 2. Okay, and this is the v part, right? This is the v part. Let's add that constant of integration at the end. Okay, let's add it at the end. So then that integral then is how much? It's gonna be x plus what we found for v. Correct? So that integral therefore that integral is equal to x plus what we found for v, which is this 1 over 8 ln of 4x squared minus 4x plus 3 minus 1 over 4 square root of 2 arctan of 2x minus 1 divided by square root of 2. Right? And let's add that constant at this stage, the constant of integration. Feel free to rationalize the denominator. If you rationalize this denominator, you get square root of 2 divided by 8, right? Okay. But this is as good as an answer. Okay? All right. So let's now step back for a second and understand what we've been doing. So don't forget, we started by just saying if the rational fraction is not proper, then you can write it as proper by using long division, right? Proper fraction. And once it's proper, those 3 lines tell you that you're going to be able to write it as a sum of simpler fractions, named partial fractions. Correct? So this happened earlier in the discussion. And once you get to this point, the next step is to factor out q of x. You're going to factor it out as product of linear factors and irreducible quadratic factors. So there are 4 cases that may occur. Case number 1 was the denominator, when you try to split it, it factors completely as distinct linear factors. This is case 1. Case 2, let me just try to find it. So case 2 was the denominator splits as product of linear factors, but some of which are repeated. This was case 2. And then we got to case 3. Among those factors, you have an irreducible quadratic factor, or you have irreducible quadratic factors, none of which is actually repeated. And the last case, as you may guess, is what if some of them repeat, right? so contains repeated irreducible quadratic factors. Let's say that this factor here, ax squared plus bx plus c, is irreducible and is repeated k times. Okay? So let's say that it's repeated k times. Now, that's case 4. So the partial fraction theorem says, instead of having the single partial fraction, right, which used to be ax plus b divided by this guy, now we're going to have a very similar thing to case 2, but now for this irreducible quadratic factor. So we're going to have, just focus on the denominator for a second. You're going to have this guy, ax squared plus bx plus c, the irreducible guy, and you're going to have downstairs k, you're going to have k denominators where each time you're going to increase the power by 1. So from 1 all the way to that k. Okay? And then upstairs, all of these guys upstairs are going to be of degree 1. Okay? So like in case 2, if you remember, in case 2, let me take you there. This is case 3. Case 2. So if this linear factor repeats k times, well, what we're gonna have is we're gonna have that factor, which is the same, but now going from 1 all the way to k, right? From 1 all the way to k, but each time upstairs is gonna have just a pure constant, correct? Over here in case 4, very similar, but instead of having upstairs a constant, it's gonna be now a linear factor upstairs of degree 1. Okay, so we're gonna have that irreducible guy, ax squared plus bx plus c, from 1 all the way to that number k that occurs, the number of times it's repeated, and upstairs they're all linear factors. So it's gonna be a1x plus b1, a2x plus b2, etc., akx plus bk. Okay. All right. So that's gonna be the partial fraction decomposition of Rx divided by Qx. All right. Example 7. This example is not about integration. It's about writing out the form of the partial fraction decomposition of this function. Okay. So the first comment is this guy is proper. Why? Because upstairs is of degree 3, while downstairs is of degree way higher than 3. Okay, what is the degree actually downstairs? It's 4 plus 2, 6, and this is 4, so 10, and this is 6, so 16, I guess, right? So this is 16 downstairs, degree downstairs, 16 degree upstairs, 3. So certainly this is proper. Okay, and downstairs, the guy downstairs is already factored completely, so you cannot factor any further over the real numbers. So here I have a linear factor repeated 4 times, here I have a linear factor repeated 2 times, here I have an irreducible quadratic factor which is repeated 2 times. This is irreducible, you can check its discriminant, it's negative, and this is another irreducible factor that's repeated 3 times. Okay, so they just want the form of the partial fraction decomposition of this rational function, just the form. Okay, so that's gonna be equal to, let's give it a name. How about f for a fraction? Actually, let's call it x because I need those letters and while writing those constants. Let's call it x. So x is equal to, let's take care of this x, the linear factor. This is case 2, right? This linear factor is found 4 times, so we're gonna have a constant divided by that guy x, and that guy x, as we said, it's gonna go from power 1 all the way to that power 4, right? The number of times it's repeated. So it's gonna have x squared, x3, and all the way to x4, right? Okay, and upstairs they're all constants, so let's call them a, b, c, and d. Okay. Okay, so this takes care of x4. Next, let's take care of this guy, x minus 1 squared. Let's change colors just to keep them, to keep it clear. So let's keep that in blue. And now for the x minus 1 squared, so what I'm gonna have is this linear factor is repeated 2 times. So I'm gonna have x minus 1 to power 1, right? And I'm gonna have that guy to power 2. Correct? This is case 2, by the way, right? For the linear factors. This is the same case I used for the x4 guy. All right, and upstairs I'm gonna have just pure constants. We are at D, so this is gonna be E, and this is gonna be F. Okay. Let's keep going. Now we're gonna move to this irreducible factor that's needed twice, 2 copies. So we're gonna have this guy. So this guy, x squared plus x plus 1, all the way to the number of times it's needed, right? And this factorization, it's 2. So x squared plus x plus 1 to power 2. And what sits upstairs? Case 4. What sits upstairs? It's linear factors, right? Linear factors. So what sits upstairs are linear factors. So it's gonna be constant x plus constant. So we're down to letter F, gx plus h, right? Similarly here, same thing. Ix plus j, right? So this takes care of this piece. And the last one is this irreducible factor x squared plus 1 to power 3. So this guy is needed 3 times. So I'm gonna have to start from this guy to power 1 and keep going all the way to this guy to power 3, right? This is case 4. I'm just using it in a naive way in some sense. So to power 3, correct? And upstairs, what sits upstairs by case 4? What sits upstairs are linear factors, right? Linear factors upstairs. So it's gonna be k x plus L, right? Mx plus N, Ox plus P. Okay? All right, where all these constants are where all these letters are constants, right? Where A, B, C, etc. all the way to P. I hope I didn't miss anything. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So they are in order. So A, B, C all the way to P are real numbers, right? So they're all real numbers to be determined. But the question didn't ask us to determine it. They just need the form. And this is the form, right? And this is the form. Okay? All right, let's move on to the next example. Let's evaluate this integral. 1 minus x squared plus 2x squared minus x3 divided by x times x squared plus 1 squared. Okay? So what do we have? Do we have a proper integral, proper fraction? Is this proper? Yes, this is of degree 3 upstairs, and it's of degree how much downstairs? 4 plus 1, 5, right? Degree 5 downstairs. Why it's 5 again? Because if you expand x squared plus 1 squared, you're gonna pick up the highest term is gonna be x to power 4 times x is gonna be x to power 5. That would be the highest or the leading term. So this is certainly proper because the degree upstairs is smaller than the degree downstairs. No need for long division, and we need to factor the guy downstairs. It's already factored for us. One linear factor, the other one is an irreducible quadratic. This is irreducible, right? X squared plus 1, you cannot reduce it anymore. And it's needed twice. Okay? So if you take that guy, we know exactly by cases 1 and 4 how to write what the partial fraction decomposition of this guy is, right? So let's write it in purple. So by cases 1 and 4, I can write this as a over x plus, for this second degree irreducible, I'm going to have one that has to do with x squared plus 1, and the other is going to be for x squared plus 1 squared, right? Correct? And each one upstairs is going to be a linear factor. This is case 4. So bx plus c and dx plus e. Correct? This is what's going to happen. Again, cases 1 and 4. Okay. All right. And obviously we need to find a, b, c, d, and e. For the purpose of the video, just to cut it a little shorter, I'm going to give you the answers. This is just algebra here. So check that. The technique is the same. Have the same denominator and then compare the numerators, right? The polynomials, and then compare the coefficients of the monomials, right? So this is how you find them. Check that a is, let me make sure I give you the correct ones. So a is gonna be 1, b is gonna be -1, c is -1, d is 1, and e is 0. Okay, so please check this. Therefore, the integral, let's give it a name instead of copying it. So the integral, how about zeta? So therefore, the integral zeta is equal to the primitive of a over x, which is 1 over x, so dx over x, plus primitive, b is -1, so negative x, c is -1, so -1, divided by x squared plus 1 dx. How do we handle this? We're going to split it in two pieces, right? One is going to have to do with ln, the other is going to have to do with arctan, plus, for the d guy, is 1, e is 0, so this guy is not there. So I have x divided by x squared plus 1 squared dx. Correct? How do we handle the last one? Direct U-substitution, right? X squared plus 1 can be thought of as u, and this becomes half du, right? Okay. All right, let's do the steps. So this is ln of absolute value of x. Correct? Okay. For the x divided by x squared, I have a minus. For the x divided, you know what? I'll do it in. I'll write everything. So minus the primitive of x divided by x squared plus 1 dx minus dx divided by x squared plus 1. I just split those two, right? Plus, can we do this quickly? if we set, I'm gonna do it mentally, but I'm gonna, along the way, I'm gonna actually write things just for you to be able to see them. If I see this as u, then du becomes 2x dx, right? So then this is gonna be half, this is gonna be half du, right? So that's gonna be half du. So it's gonna be half times half primitive of u to power negative 2 du, and u to power negative primitive of u to power negative 2 du is u to power negative 1, right, divided by negative 1. So it's gonna be minus 1 divided by x squared plus 1, and plus a constant of integration, but I'll combine everything with those constants here, okay? So this guy is the primitive of the last part, okay? Let's be very clear. So this guy and this guy are the same. This guy, maybe this color, and this guy are the same, okay, and those pieces together, okay. Okay, so can we find this by itself? This guy here, I mean, still mental U-substitution. If u is 2x plus 1, sorry, if u is x squared plus 1, so du is going to be 2x dx, so this is going to be half du, so it's going to be half du over u, which is ln of u, absolute value of u, but u is positive already, so you get this, correct? I'm doing them mentally to encourage you actually to do them mentally. Okay, I can write out the details, but we've done many, long videos on all these, and by now you should be able to do them mentally. I'm doing them in front of you to actually encourage you to do it. How about this part? You can think about 1 as 1 squared, right? And as such, you obtain 1 over a, so 1, arctan of x divided by a, so x, correct? Okay, and at the end of the day you get the following. This is going to be equal to this piece, which is ln of absolute value of x, minus half ln of x squared plus 1. Here I did not put bars because x squared plus 1 is positive, it's at least 1, right? So we obtain this minus arctan of x and minus this piece, which is 1 over 2 times x squared plus 1 plus a constant of integration at the end of the day, correct? Alright, so this is zeta, this is this integral. Alright, the last thing is I want to read this remark. So what does this remark say? Note that sometimes partial fractions can be avoided when integrating a rational function. We've encountered something like this earlier, right? Probably it was example, let me take you back there. I think it was this example, right? The one coming from the book, example 3. In finding w, we didn't have to go through the partial fraction decomposition. Remember, we could have just used a direct substitution. We discussed that. So note that sometimes partial fractions can be avoided when integrating a rational function. This is another example. For instance, although the integral that you see here, this integral that you see here, can be evaluated by the method of case 3, right? This is of case 3 and case 1, to be honest. Case 1 for this, case 3 for this. It's much easier to observe that if you set this to be u, right? If you set this to be u, and you distribute the multiplication over addition, you get x cubed plus 3x. Then du becomes 3x squared plus 3. You can factor out a 3, it becomes 3 times x squared plus 1, so the guy upstairs, right? And I forgot to write here du, correct? So this is technically du here. Okay, so the dx. So the point is, you get the dx, the du is 3 times x squared plus 1, this entity dx, so which means x squared plus 1 dx is actually 1/3 du, 1/3 du, and then so it becomes 1/3 du over u, right? And 1/3 du over u is 1/3 ln of the absolute value of the u, and that's the u, right? Plus a constant, where this constant is an arbitrary real number. So what this is saying is, keep in mind that partial fractions, I mean, even though it works for these type of rational functions, it may be avoided and actually shortcut the way to your answer, to the answer. Okay. All right. So by this we complete the current section, which was about partial fractions. So it's about integration of rational functions by partial fraction decomposition.